What is chemistry? That you can give me a part of it. You don't have to give me the whole definition. What does chemistry involve? Anyone? Molecules, atoms, elements. What else? Reactions. Bonds. Anyone else? These are all things that we are going to talk about this semester. But this is all part of what we'll be learning, but the actual definition of chemistry is pretty vague. And I got this straight from Wikipedia. So chemistry is the study of the composition, properties, and change of matter. Now, what you all just told me is involved in this, right? So the composition, molecules, atoms, elements, that's all the composition, right? And then properties, maybe how they bond together and how they react. And then change, reactions, is the change of matter. So we'll be talking about all of this and more. So can anyone tell me, though, what matter is? What is everything made up of? Atoms, right? So matter is made up of atoms. It takes up space. And has mass. So there's no matter in our universe that we know of that doesn't take up space and that doesn't have mass. We know there's a lot of matter we don't really know what's going on with, like dark matter. We're not really sure what it is. We know it makes up a lot of our universe, but we're not really clear. But it has mass and it takes up space. And it, honestly, that we don't know if it's made up of atoms, but we'll see. You know, that's one of the things. But right now, our definition of matter is it's made up of atoms, it has mass, and it takes up space. Now, what is an atom? Anyone? Yeah.
You mean like the parts that make up an atom?
Well, so an atom is made up of protons, neutrons, and electrons. But the thing about what's so special about the atom is it's the smallest unique particle that makes an element special, right? It gives elements its properties. So it's the smallest unique particle that gives an element its properties. So yeah, you are right. It's made up of smaller particles, and those particles are made up of even smaller particles like quarks and antiquarks and all of that. But when it comes down to it, an atom of gold and an atom of carbon are both made up of protons and neutrons and electrons. So those aren't unique to the element, but the amount of each of those smaller particles that make up the carbon atom and the gold atom are different, and that the relationship, the numerical relationship between those protons, neutrons, and electrons is what makes each of those elements unique. One more definition here. What is a molecule? What is a molecule made up of? Atoms, right? Yeah, we just talked about it. So a molecule is just more than one atom bonded together. And I'm just starting out with these definitions. so we have a context for what we're going to be doing in the next couple weeks. What we're going to be doing in the next couple weeks is a lot of math and a lot of conversions. You might be like, why is this chemistry? But the tools we will be using in the next couple of weeks, we will use throughout your chemistry or your scientific career if you go on in science. And the study skills and the thinking skills that you learn, you can use in other fields as well. Okay, does everyone have this? All right, let's move on. I want to talk about the scientific process and scientific thought. So I'm calling it this. I'm not calling it the scientific method, because the scientific method is a specific set of steps, right? You have observation, hypothesis, experimentation. And while that is an excellent method, it's used by a lot of scientists, not all scientific research is hypothesis driven. Some of it is discovery driven, where you just go in and you say, I wonder what's going to happen if I do this. You have no idea what's going to happen. And you just kind of try different things until you find something, and you make observations based on that. So not all scientific research follows that nice, clean, stepwise observation, experiment, hypothesis. And sometimes it's a really circular process, right? You might make some observations, you might have a hypothesis, you might experiment, but then you don't really get results. So you need to go back and you need to alter your hypothesis and you need to run more experiments, right? It's never as simple as observation, hypothesis, experiment, results. But the scientific process is, I'm just giving you a lot of definitions right now, and then we'll move on to actually working through some problems. But right now, I just want you to have these in your head. So it's investigating natural phenomena, acquiring new knowledge, correcting and integrating previous knowledge, and that's a really important part, which I'll expand on later, through testing, reasoning, and other problem-solving techniques. And this is really important now, since there are so many questions in our country about science and politics. And I want you to be able, even if you don't go on in sciences, even if you take this for B1, just to be able to come out of this class with a sense of how to think about science and how to judge for yourself about whether something might be, pop science, or it might be able to be disproven, or whether real solid scientific fact. And also the fact that scientific facts can always be disproven. They are well substantiated, but there's always a chance that something will come along that we don't know about, and a new circumstance will change the way we think about how the world works. That is something that has happened throughout the history of science. And there are a couple of more terms that I want you to know, and one of them is scientific law. It's important that you know what a scientific law is, because generally we think of laws as something that shouldn't be broken. Scientific laws can be disproven, but scientific laws are statements based on repeated experimentation and observation, and they describe some aspect of nature. Oops. and they can be disproven or altered. Now, an example of this is the conservation of mass, the law of conservation of mass. In most cases, especially when you have a reaction, pretty much all the cases that we're going to be talking about in our class, what you put in, this word is altered. Sorry about that handwriting. What you put into a reaction will generally, in terms of mass, how much you put in, how much that weighs, that's generally how much you will get out of it in terms of mass. And for a long time, for a few centuries, everyone thought, all scientists thought that was how it always worked. Mass can neither be created nor destroyed. But then a guy named Einstein came along, and he came up with the energy mass equivalence, which you know more commonly as E equals mc squared. And in some circumstances, energy and mass can interconvert. You can change something from energy to mass. So even though conservation of mass doesn't apply in some special circumstances, and sometimes it can turn into energy, we still keep around the conservation of mass, law of conservation of mass, because in most circumstances in our everyday lives, that's how the world works. And we can do those calculations, especially in a class like this. We won't be using E equals mc squared. If you go on to quantum chemistry, that's something you would use, but we don't have to worry about that here. So even though law of conservation of mass was disproven in some cases, we still keep it around because it is useful in certain circumstances. One more definition is scientific theory. Once again, this term is something, it means something different in science than it means in everyday life. In everyday life, we think of a theory as maybe an educated guess. In science, it's much more than that. It is a well-substantiated, so once again, based on lots of experiments and observations, explanation of natural phenomena but once again, this can be rejected or modified. And we have seen this as well. Newtonian mechanics is a theory that describes how things move, how if you throw a baseball, you will be able to predict where it will land based on Newtonian mechanics. However, when you get down to the atomic level, Newtonian mechanics breaks down, which is why we have quantum mechanics. However, even though Newtonian mechanics doesn't work in every situation, we still use it in physics classes, because if you tried to describe the trajectory of a baseball using quantum mechanics, it would be incredibly complicated. You could do it, but it would be a lot of work and it would take a lot of calculation. It's much easier to do it using the equations we have in Newtonian mechanics. So once again, just like a scientific law can be kept around even though it's been rejected for some circumstances, so can a scientific theory. Now, the scientific law and the scientific theory have pretty similar definitions, but one is a description and one is an explanation. So a law is what, and a theory is why. Questions thus far? And now that I've talked about the scientific process and the scientific theory and scientific laws, we are going to start using tools. We're going to go into some of the tools we can use in the sciences, such as scientific notation and significant figures and why we use those and how we do those. Does everybody have this? All right. Scientific notation. I abbreviate scientific notation as SN, especially on exams. So if you ever get, you know, a point marked off and it says SN, it's because your scientific notation isn't correct. So that's the notation there. I just want to make sure that you know that SN means scientific notation. Does anybody know why we use scientific notation? Yeah, so make it easier to write very small and very large numbers. It saves space. And then also on your worksheet, you'll do something using scientific notation where you use it where you write it on the axis of a graph. It saves space when you're doing scientific graphs with data and things like that. So the format of scientific notation is times 10 to the. So if you have the number 80, this is going to equal 8 times 10 to the 1. Because that just is 8 times 10. 10 to the 1 is 10, so 8 times 10 is 80. 8,000 is 8 times 10 to the 3 because 8,000 equals 8 times 10 times 10 times 10. Instead of figuring it out this way, we can count where the decimal moves to in order to determine what that exponent will be. If you have, once again, 80, imagine there's a decimal that would be right here. And we have to move that over 1 to put the imaginary decimal behind the 8. So because you moved it over 1 spot, your exponent is 8 times 10 to the 1. And any number that is greater or equal to 10 has a positive exponent. Positive exponents, the larger the positive exponent, the greater the number. With 8,000, we can do the same thing. We imagine there's a zero right behind that, a decimal right behind that last 0. We move it over 3 places to be right behind the 8. And because you moved it over 3 times, and this number is a positive exponent because it's a number larger than 10, it is 8 times 10 to the positive 3. Questions thus far? I'll talk about negative exponents in just a second, but I want to first talk about when you don't move this decimal at all. If you have just the number 8, if I ask you to write that in scientific notation, that's just 8 times 1, right? So 10 to the what is equal to 1? 0. So when you don't move the decimal at all, you just put 8 times 10 to the 0. So a number between 1 and 9.99 will have just 10 to the 0. Let's talk about negative exponents. The more negative the exponent, the smaller the number, right? So if you have 10 to the minus 24, that's 0.23 zeros, and then you have a number. And the way we do that is 0. So we start with 0.8, And that is equal to 8 divided by 10, which is equal to 8 times 10 to the negative 1. Because if you divide by a number, that is to the negative 1, that number to the negative 1. If we take this even farther and we go 0.008, that's equal to 8 divided by 10 times 10 times 10, which is equal to 8 times 10 to the negative 3, because you divided it by 10 3 times. Numbers that are less than 1 have a negative exponent. So if you have a decimal and then your first number, that is a negative exponent. That doesn't mean the number itself is negative, it just means it's a small number. And once again, we can count what our exponent is by moving that decimal. 0.8, you want to have this decimal behind the 8. You move it once, and because it's a number smaller than 1, your exponent is negative 1. Same with this, 1, 2, 3, to have your decimal behind the 8. 8 times 10 to the negative 3. Now, it's not always just going to be one digit. Sometimes you'll have, for example, 9.65 times 10 to the negative 4th. In that case, you're going to write it, is it a large number or a small number? Small number. So it's going to be less than 1, and it's going to be 0.000965, because you don't look at the last number, you look at where the decimal moved to. So you move that decimal 1, 2, 3, 4, because you moved it 4 times, and it's a very small number, less than 1. It's going to be, the exponent is going to be negative 4. Questions? In the opposite direction, we could have 3.265 times 10 to the 5th, which would equal 32650, because remember, it's all about where the decimal is. You move that decimal 1, 2, 3, 4, 5 places, and it's a big number. It's greater than 10. It's greater than or equal to 10, so it's a positive 5 exponent. Oh, and if you're in the back row and you're having problems seeing the board, you know, I don't have great eyesight. So you are always welcome to move forward. These are not assigned seats. So just know that if this first day sitting in the back row doesn't work for you, move on forward the next class. So this exponent, the difference between times 10 to the negative, times 10 to the 4th and times 10 to the 5th, we call that a difference of an order of magnitude, okay? So every time you multiply by 10 or divide by 10, you're increasing by an order of magnitude or decreasing by an order of magnitude, okay? So 10 to the 5th is 3 orders of magnitude higher than 10 to the 2. So if I say that, that's what I'm talking about. There are incorrect ways to write scientific notation. So for example, this. What's wrong about this?
Decimal's in the wrong spot.
Decimal's in the wrong spot because you only want one digit in front of the decimal. I see that we have 10 to the 3rd. I have 25.2. We want it to look like 2.52 times 10 to this something. Okay, so we need to figure out what that number is. Notice that 25.2 is 1 order of magnitude higher. So we're going to have to move that exponent up to 10 to the 4th if we move our decimal down. Oh, sorry, I'm writing it. This should be in the correct column. There we go. 2.52 times 10 to the 3rd. I mean, sorry, 4th. So because 25.2 is an order of magnitude higher than the number we wanted for that decimal, you have to increase the exponent to make up for the fact that we moved that decimal. Okay? So these are the same number. They're both equal to 25,200, yeah. But one is in correct scientific notation and one is in incorrect scientific notation. You can also go the opposite direction. So if I have 0.0049 times 10 to the 6th, are we going to move our exponent up or down? Are we going to, is it going to be greater than 6 or smaller than 6? Smaller. Because this number is 3 orders, you're going to have to move the decimal 3 orders of magnitude. It's a smaller number. You're going to have to move that decimal, that exponent down. So we move the decimal 1, 2, 3 times. And because that's a much smaller number than 4.9, it's going to be 4.9 times 10 to the 3rd. So we had a number that was 3 orders of magnitude smaller than what we want, which means that we have to move our number down to 10 to the 3rd. Questions? We will have practice on this in our worksheet. Let's do a little practice. So you're going to write 69,800 in scientific notation. You're going to write 2.65 times 10 to the minus 6 in standard notation, which is just normal notation, how you would not write it if it weren't in scientific notation. And then write 0.62 times 10 to the 4th in correct scientific notation. And if you have any questions, please raise your hand. Chris and I are here to help. Yes, excellent question. I will talk, if I have time, I will take that at the end of time. Yeah. All right, can anyone tell me what number 1 is? .98 times 10 to the 4th. She moved her decimal 1, 2, it's a big number, it's more than 10, that means that it's a positive exponent. How about the second question? Anyone else? Yeah. Yes. Yes. 5 zeros. So she moved her decimal 1, 2, 3, 4, 5, 6 places. It's a very small number. That means it's a negative exponent. That's correct. And how about this last one? 6.2 times 10 to the third. So because it's a smaller number than 6.2, we have to move that decimal down over 1. Where am I? Yes, over 1. And so that means because it was a smaller number, that exponent goes down. Questions, concerns? Once again, we will have a worksheet that we practice with this. All right. Let's move on. Oh, there's one more thing I want to talk about in terms of scientific notation, and that is let's everyone take out your calculators. Always bring, if you don't have it, that's fine for today, but always bring your calculator to this class. It can be a scientific or a graphing calculator. Never forget it, especially on an exam day, because I will not have extra calculators on exam day. You will have to run and get one from somewhere. If I wanted to enter 8 times 10 to the 6th in the calculator, does anybody know what the scientific notation button looks like? It has 2 E's on it, EE. Sometimes it is a second function. So for example, yeah, yours is a second function, fine. A lot of people have this calculator. I'm going to use this as an example. In this case, it's a second function x to the -1. I was reading that down. Some of you, most of you should have that button. If you don't have a calculator with that button, I would highly recommend getting a different calculator. And the reason that button is really important is because if you use that button and know how to use it, it will make your life so much easier. It will make your calculations so much easier. Because if you put 8 times 10 to the 6th in a calculator, you have to put parentheses around the whole thing in your calculation, especially if you're dividing by that number, or else it will completely mess up the calculation. So if you enter it with the scientific notation button, you don't have to use parentheses. It's really easy. So what the EE button, so when you enter this, it would be 8EE6. That EE is times 10 to the, okay? That takes away all of that extra. EE, if you enter 8 EE button 6, that is 8 times 10 to the 6th. It will show up in your calculator as 8E6. You can also write your scientific notation that way if you know how to do it, but just know what you're doing. But I do accept that on tests if you know how to write scientific notation with just the E. Questions on that? And I always welcome if you don't get the same answer as me on a problem, raise your hand or talk to me after class, because a lot of the time, a lot of the mistakes I see on tests especially are calculator errors. We're going to do a lot of work on looking at your answer and knowing whether it's a reasonable answer or not, because, for example, if I give you a problem and it talks about an ant, and you end up seeing with an answer that ant weighs 10 to the 3rd kilograms, that's not correct. So maybe take a look at the math you did, okay? Because an ant would be along the lines of micrograms or milligrams, okay? So you always want to make sure that you're kind of aware of the scale of your answers and aware of whether it makes sense or not. You can also, in certain calculations, in order to determine whether you got the right answer, it's just a quick check. Know that you can divide 10 to the whatever by 10 to the whatever, you can cross that out. Because, for example, if you have 6 times 2 times 2, right, over 6 times 2, you can cross out the 2 and the 2, okay? So, or 6 times 4 and 6 times 2 on the bottom, you can cross that out. Similarly, if you have 6 times 10 to the 5th over 2 times 10 to the 3rd, this 10 to the 3rd can cross out, and you just reduce this by 3. So 3 of those 10s cross out because you're multiplying 10 times 10 times 10, and on the top you're multiplying 10 5 times. So that will cross out, and you will have just 10 to the 2. Your answer then will be 6 times 10 to the 2 over 2, which is 3 times 10 to the 2. Because there, you can just divide these numbers here. You won't have to do it this way on a quiz, but this is a really good way of understanding whether your answer makes sense, because if you go through your problem and you see that you have 10 to the 5th on the top and 10 to the 2 on the bottom, and your answer ends up being 10 to the 7th, that's not correct. So you want to make sure that you kind of understand how those 10s cross out, how those exponents cross out. Let's talk about significant figures. There are 4 rules to significant figures. Number 1, and we will talk about why we use significant figures after I give you the 4 rules. Just write these down. These are very important. Never forget them. I am teaching a 111 discussion class, so that's 2 semesters ahead of you if you go on in the sciences. And I'm still talking about significant figures. So this is not something that I will let you forget, that Catherine, who teaches 110, or John, who teaches 111, will let you forget. Significant figures are important. Rule number 1 is that non-zero, I write my Z's kind of like, what do you call it? Cursive, yeah, thank you. Non-zero numbers are always significant. That means that 36, which has 2 non-zero numbers, has 2 sig figs. Yes, I also abbreviate sig figs, or significant figures, to sig figs or SF. So if on a test you get something marked down and it says SF, it's because your significant figures were incorrect. The second rule is that zeros between non-zero numbers are always significant. Which means that 306 has 1, 2, 3 sig figs because that 0 is between 2 non-zero numbers. Rule number 3, zeros to the right of non-zero numbers are significant only if a decimal is present. And it doesn't matter where the decimal is. It just matters that there's a decimal somewhere in the number. which means that zeros to the right are also called trailing zeros because they trail off at the end. So if you have 3.60, there is a decimal in that number, which means that trailing zero is significant. 1, 2, 3 significant figures. $3.60 does not have a decimal, so is that trailing zero significant? No, because it's only significant if there's a decimal present. So this only has 2 significant figures. $360.0, there's a decimal present, so how many significant figures does this have? 4. Both trailing zeros count. Doesn't matter where the decimal is, if it's between the zeros or after. 1, 2, 3, 4, those all count. So we have 4 significant figures. Our fourth and final rule, zeros to the left of non-zero numbers are never significant. Also known as leading zeros. Zeros to the left are leading zeros. 0.033, based on this, how many significant figures do we have here? 2. Because we have 2 non-zero numbers, the 3 and the 3, and the 2 zeros there are leading zeros. They're zeros to the left. Once again, doesn't matter where the decimal is, they're leading zeros. They do not count. So we only have 2 sig figs. Now I'm going to combine rules 3 and 4. How many sig figs do we have there? 0.330. 3. Because leading zeros never count. Trailing zeros count if there's a decimal. So only this 0 counts, and then the 2 3s. So we have 3 sig figs. Can anyone tell me why we use significant figures?
For scale.
Sort of. Yeah, it's like kind of how well you know it on a certain scale. A better word for that would be precision. How exactly you know a number. So for example, 360 has only 2 significant figures. That means that we only know this number to the tens place. That means it's about 360. It could be 357. It could be 361. We don't know exactly what this number is, so we only can be sure to this significant figure. So it's about 360. However, this number is the same value, but we know it more exactly. We know it's exactly 360.0. We know that very well. We know it's the tenths place. So even if you have the same number, you can know it, this number sort of, and this number, it's exactly 360. So if you have, for example, a TV show, and they say, and the TV company says, 2,560,000 people watch this particular episode. That's an estimate. That's not exactly 2,560,000 people with a decimal at the end. That's saying it's about 2,560,000, based on how we get our data, and that's, we know that to the 10,000 place. Okay, so it could be 2,562,000. It could be 2,559,000, something like that. Another example of this is in the Olympics. In the 100-meter race, we know the times to the millisecond. Okay, so we know to the 0.000. However, in swimming, so there's hardly ever a tie in the 100-meter race because we know it so exactly. In swimming, however, especially if you watched last summer, there were several ties in various races. Simone Manuel tied for first place. And that was a tie because in swimming, we only know it to the hundredth of a second. So if someone swims 100.20, that beats 100.21. However, if you have someone who swims 100.213 and someone else who swims 100.211, that last significant figure, we don't know that. So they're going to tie because both of those round to 100.21 seconds. Any questions on this? All right, let's do the worksheet.